The smoothing spline is a method of fitting a smooth curve to a set of noisy observations using a spline function. Definition: let be a sequence of observations, modeled by the relation. The smoothing spline estimate of the function is defined to be the minimizer of remarks, is a smoothing parameter, controlling the trade-off between fidelity to the data and roughness of the function estimate. The integral is evaluated over the range of the as the smoothing spline converges to the interpolating spline. As the roughness penalty becomes paramount and the estimate converges to a linear least squares estimate. The roughness penalty based on the second derivative is the most common in modern statistics literature, although the method can easily be adapted to penalties based on other derivatives. In early literature, with equally spaced, second or third order differences were used in the penalty, rather than derivatives. When the sum of squares term is replaced by a log likelihood, the resulting estimate is termed penalized likelihood. The smoothing spline is the special case of penalized likelihood resulting from a Gaussian likelihood. Derivation of the smoothing spline: it is useful to think of fitting a smoothing spline in two steps. First, derive the values. From these values, derive for all x. Now, treat the second step first. Given the vector of fitted values, the sum of squares part of the spline criterion is fixed. It remains only to minimize, and the minimizer is a natural cubic spline that interpolates the points. This interpolating spline is a linear operator, and can be written in the form where are a set of spline basis functions. As a result, the roughness penalty has the form where the elements of A are the basis functions, and hence the matrix A, depend on the configuration of the predictor variables, but not on the responses or. Now back to the first step. The penalized sum of squares can be written as where minimizing over gives de Boer's approach. De Boer's approach exploits the same idea, of finding a balance between having a smooth curve and being close to the given data. Where is a parameter called smooth factor and belongs to the interval, and are the quantities controlling the extent of smoothing. In practice, since cubic splines are mostly used, is usually the solution for was proposed by Reinsch in 1967. 4. When approaches, converges to the natural spline interpolant to the given data. As approaches, converges to a straight line. Since finding a suitable value of is a task of trial and error, a redundant constant was introduced for convenience. Is used to numerically determine the value of so that the function meets the following condition. The algorithm described by de Boer starts with and increases until the condition is met. If as an estimation of the standard deviation for, the constant is recommended to be chosen in the interval. Having means the solution is the natural spline interpolant. Increasing means we obtain a smoother curve by getting farther from the given data. Creating a multidimensional spline. Given the constraint from the definition formula, we can conclude that the algorithm doesn't work for all sets of data. If we plan to use this algorithm for random points in a multidimensional space, we need to find a solution to give as input to the algorithm sets of data where these constraints are met. A solution for this is to introduce a parameter so that the input data would be represented as single-valued functions depending on that parameter. After this, the smoothing will be performed for each function. In a bidimensional space, a solution would be to parameterize and so that they would become and where. A convenient solution for is the cumulating distance where. A more detailed analysis on parameterization is done by E.T. Wiley. Related methods: smoothing splines are related to, but distinct from, regression splines. In this method, the data is fitted to a set of spline basis functions with a reduced set of knots, typically by least squares. No roughness penalty is used. Penalized splines. This combines the reduced knots of regression splines, with the roughness penalty of smoothing splines. Elastic maps method for manifold learning. This method combines the least squares penalty for approximation error with the bending and stretching penalty of the approximating manifold and uses the coarse discretization of the optimization problem. See thin plate splines. Source code for spline smoothing can be found in the examples from Carl de Boer's book A Practical Guide to Splines. The examples are in Fortran programming language. The updated sources are available also on Carl de Boer's official site. 1. Further reading, Lochba, G. Spline models for observational data. Siam, Philadelphia. Green, P.J. and Silverman, B.W. Non-parametric regression and generalized linear models. CRC Press. De Boer, C. A Practical Guide to Splines. Springer. References